Hello. Oh, welcome to video 2 from section 2.1. Yeah, last time we talked about multiplying matrices of agreeable sizes. Sort of important. So if we want to multiply matrix A and B, we needed that A is something by n and B is n by something. So these two dimensions need to agree for the multiplication to make sense. And the result is an m by k matrix AB. And so we have a theorem here, theorem 2.2, which basically says that matrix multiplication obeys many of the typical, properties of multiplication that we would expect to have. So if A is m by n and B and C are indicated sizes, if we multiply A or B and C by A, or B C by A, or AB by C, those two things are equal. So it doesn't matter how you parenthesize or bracket the multiplication. And here we need what? We need that A and B can be multiplied together, so those two dimensions need to be the same. And we need the B and C to be multiplied together, so those dimensions need to be the same. And similarly, if you multiply A by the matrix B plus C, it doesn't matter. Yeah, it's equal to AB plus AC. So you're distributing the way you would with the numbers. And again, here we need B and C to be the same size, n by k. And you can do that on the right or on the left, same deal. If we have a scalar times a product of matrices, that's the same as hitting either one of the matrices with that scalar. And then, if you do the identity matrix times A, that'll be equal to A, which is equal to A times the identity matrix. And again, here we need the identity matrix to be n by n. Here we need it to be m by m, because we know that A is n by m. Okay, and I made this note last time, but I will say it again. So most of the expected properties of multiplication are true. Most of the expected properties of multiplication are true. But absolutely not that AB is equal to BA. That is just not true. Let's do this. Let's look at an example. We've seen some examples before. Let's look at another example for how this fails, because it's almost never true. Okay, let's take A to be 1, 2, 3, 4, my favorite matrix. We'll take B to be 2, 5, -1, 3. We can compute the product two ways, or two products, A, B, and BA, and we'll see not equal, just not equal. No two ways about it. 1, 2, 3, 4, 2, 5, -1, 3. Okay, so this is 1 times 2 plus 2 times -1. This is 1 times 5 plus 2 times 3. Here we've got 3 times 2 plus 4 times -1. And then finally, 3 times 5 plus 4 times 3. And so we get back 0, 11, 2, 27. 7. Okay, that's AB. BA is, just the reverse. Well, I'll save you the long computation. We get 17, 8, 24, 10. So not equal. Hopefully getting the message. Okay. What else is not quite true? Let's insert another page here. Oh, boom. Another tempting property that we now have from real numbers that no longer works. Check this out. Okay, here we go. Observe is the fancy way of saying check this out. If we have got 1, 1, 2, 2, we can multiply this by the matrix 1, 1, -1, -1. What are we going to get? 1 times 1 plus 1 times -1, that's 0. 1 times 1 plus 1 times -1, okay, that's 0 again. 2 times 1 plus 2 times -1, that's 0, and 0 here too. So we can have two non-zero matrices multiplied to get a zero matrix. So AB can equal to 0 without either A being 0 or B being 0. This is not true for real numbers, not true for our regular multiplication, but it's true for matrices because because it's more complicated somehow. And so as well, or similarly, we can have AB being equal to AC without B being equal to C. Even if A is non-zero. So there are some subtleties to multiplication. We can't use all the techniques we're used to using. Which ones can you use? That's exactly what the theorem is saying. Here are the typical properties of multiplication that are alive and well. Here are some ones that no longer with us. We can't use any longer. All right. The next thing I wanted to introduce is the transpose. So if you have a matrix A, its transpose AT is just the matrix you get if you swap the rows for columns in your matrix A. So let's look at if A is the matrix 1, 2, 3, 4, 5, 6, then the transpose should just be the matrix you get when you make each row a column. So if you make the first row a column, it becomes 1, 2, 3. If you make the second row a column, you get 4, 5, 6. And there's your transpose. You just rotate things around to make your rows columns. And that gives us the next little theorem, which is basic properties of transpose. So if you do the transpose twice, you get back to where you started. That should be sort of obvious. If you take the sum of things, the transpose of the sum of things, that's the same as taking the other transpose, and then taking the sum. If you have any scalar number R, the product of R with A, then taking the transpose is the same thing as just taking the transpose first and then multiplying by R. And then the only one that's sort of counterintuitive is if you take the product of two matrices and its transpose, that should be the product of the transposes in reverse order. That's the part that's maybe hard to remember. And I'll explain why that's the case. Why isn't it A transpose times B transpose? There's lots of reasons, but the first one is, well, let's look at the sizes of A and B. It's certainly whatever this is equal to, it can't be equal to this because the sizes of A and B aren't going to work out that way. If A is M by N and B is N by K, then certainly we can take the product AB because our N and our N's agree. But what's the size of A transpose? Well, if you're making all of the columns rows and rows columns, then you should just swap those sizes. So A transpose is N by M, and B transpose is K by N. So definitely we can't multiply A transpose and B transpose because these dimensions don't equal. Although we can multiply B transpose and A transpose. So A transpose B transpose doesn't make sense, but this one does, and it happens to be equal to the thing we want. And why is that the case? Excellent question. Check out the textbook for a complete answer. I think that's all we want to talk about in this section. So I'll see you all next time with section 2.2. Take care, everybody.